focused on a very interesting topic. The focus of my talk will be persistent switching and memory effects in vanadium dioxide. So far we observed three types of persistent effects in this material. Electrostatic switching in gated structures with CO2 being an active semiconductor. Memory resistance driven by current pulses. This electrostatic switching is work of Basov. Memory resistance and memory capacitance is work of Tom Driscoll, who is here in collaboration with Mark. I will spend most of my time discussing physics underlying these switching processes, and it's all of these effects you believe are intertwined, and they are all connected to the insulated metal transition that vanadium dioxide undergoes just above the room temperature. Through Parkin yesterday discussed some aspects of this transition, and I will talk more about it. I won't claim that we understand this transition very well, but we are trying to make progress, so this work will be a progress report of some time. We investigated structural aspects of this transition with an X-ray nanoimaging, and we investigated in quite detail electronic aspects of this transition using infrared nanoimaging. And I will tell you a little bit about this technique because this tool allows, appears to may enable studies of many other memory resistance implementations that we discussed, that were discussed in this workshop. Because essentially every switching device implies some kind of non-uniform distribution of conductivity, and that's precisely what we can pick up with this technique. So all these experiments seem to suggest that the phase separation plays a critical role in switching phenomena that we observe. And in the end, I will summarize and I will outline some of the unresolved issues. It's a pleasure to acknowledge my collaborators. All memory resistance and memory capacitance work is the work of Tom Driscoll, who is here. Kazelbach worked on electrostatic devices. Analysis of many of these images has been done by Alex Frenzel, who was an undergraduate in my group and is now with Jimmy Hoffman at Howard. Structural work has been carried out in collaboration with Oleg Shpirko, my colleague. We've been working on VO2, on metal insulated transition in VO2 for quite some time, but all this new angle, memory angle on the problem really originated from numerous discussions with Maximiliano Di Ventra. Near-field optics is a technique that we've learned from Fritz Keilmann in Munich and Martin Brem, and this work would not have been possible without our collaborators in Korea. A group of Unitam team at ETRI has provided all samples for this work. Some introductory remarks about VO2. Its unusual properties have been discovered quite some time ago, in 1959. This diagram is from the paper by Morin, reporting the metal insulated transition in several oxides. In better films or crystals, resistivity changes can exceed 3 orders of magnitude, and pretty much everything in the electronic transport of VO2 is quite exotic. For example, resistivity shows this linear temperature dependence up to 900 Kelvin, maybe 1000 Kelvin, and if you start extracting the mean-free path from this resistivity, you'll find out that it's shorter than interatomic spacing. This is the behavior coined bad metal behavior by Emery and Kivelson. A closely related compound, V2O3, is a canonical example of a mod insulator. Unlike V2O3, vanadium dioxide does not order antiferromagnetically. Instead, it forms these vanadium dimers in the insulated state, and this prompted the interpretation of the transition in terms of spiral speed. It's evident that this dimerization is gone on the metallic side. And so the debate whether this is a Montre insulator or a Pyros insulator has been going on for quite some time. And new experimental tools and new theoretical tools are uncovering previously unexplored aspects of this transition. And if you go through the recent literature, you'll discover that VO2 is very much at the vanguard of what's going on now in condense matter physics. One roadblock towards understanding this transition is that structural changes and electronic changes occur more or less simultaneously. And it's very difficult to identify what's the cause and what's the effect. And in order to approach this problem, we try to fabricate gated structures with VO2 as an active semiconductor, and we were hoping to tune the insulated metal transition electrostatically. So this is a cross-section of the device. This is a photograph of the transistor. Doesn't look pretty, but it works. We used plastic insulators in this device. It's a parallel insulator, and in the past we have studied other gated structures with these type of insulators in great details. An advantage of this insulator is that you can deposit it at room temperature, and yet this insulator sustains the electric field matched only by silicon dioxide. And then we illuminated this device. It has a transparent gate electrode. We illuminated it with infrared light, and we interrogate what's going on in the active layer using optics. Unfortunately, the substrate, aluminum oxide substrate, is such that it blocks most of transmitted radiation, and it only leaves us a window below 200 wave numbers. And optical constants of VO2 are such that there is really not much is going on below 200 wave numbers. That's about 20 millielectron volts. And instead of showing you featureless spectra, I will show integrated absorption. And this quantity is significant because, according to modal independent sum rules, this integral of absorption is proportional to the number of charges participating in absorption. And you see that this number of charges is increasing systematically with the applied gate voltage. This effect is particularly strong on the cold rolled side of the polarity of the applied gate voltage. There are some deviations from the linearity here. I don't know if they're significant or not. Note that in this experiment, we really interrogate VO2 physics only with light, and there is no current flowing between source and drain electrons. In fact, we keep them at the same potential, and that's very important for physics. It's important because current, if it flows through VO2, can be heating it, can be switching it. So there is no heating involved in this experiment, and yet there is a clear sign of increased absorption, which is the signature of enhanced metallicity in these devices that is particularly prominent on the cold gold side. So all of these experiments are more or less conventional. What was many other gated structures would behave like this. What was unusual, what turned out to be unusual, is that this state with enhanced metallicity turned out to be persistent. When we removed gate voltage, VO2 remained in this state, and that certainly was very unusual. And when we first saw that, we didn't really know what to make out of this, but the effect was reproducible, so we reported it. It turns out that electrostatic switching is not the only persistent VO2. Current pulses also can cause lasting changes in electronic properties of VO2, and this is the work of Tom Driscoll. So this is resistivity data that he has obtained close to the metal insulated transition. And if he applies a current pulse, he can switch resistance to a lower state, and then it stays at this wave for pretty much as long as one cares to wait. And if you apply another pulse, you can switch to even lower value. And the huge dynamic range of resistance changes close to transition allows you to implement really an incredibly large number of these persistent state. Here, these pulses are pretty strong, and so the resistance changes are also small, but they don't have to be that strong. One can implement multiple reconfigurable states of vanadium dioxide. So what is the origin of these persistent transformations of the electronic state that we observed in gated structures and in these current-driven devices? So clearly, both effects are linked to the insulated to metal transition. And in order to get a panoramic view of the transition, we also examined the optical constants of VO2 across the transition. So this panel shows the real part of the conductivity that we can extract from optical measurements. Real part is the dissipated part of the conductivity, so these spectra cover the loud absorption channels associated with various excitations that you have in your system. And in the insulating state, the dominant in the DC, in the limit of zero frequency, this is just the DC conductivity that one can measure with a multimeter. So in the insulating state, the dominant reaches this energy gap, about 4,000 wave numbers, that's about half electron volt. As we warm up these samples, there is no signs of diminishing energy gap. Instead, this low energy spectral wave is filled up with states, and eventually, through the conductivity, emerges out of this intergap property. These spectra, if you spend a lot of time in your life staring at spectra like this, they will tell you that the system, the spectra look, are very similar to many other materials that are phase separated. Very clear sign of electronic phase separation is seen in the temperature dependent of the real part of the dielectric constant that we can extract from this data. You can observe nearly divergent behavior of the dielectric constant at the boundary of the transition. And this is more or less what you would expect to have a system with metallic puddles embedded in insulating coatings. Various researchers have suspected that VO2 may be phase separated. In fact, phase separation is a commonplace in transition metal oxides, but until recently, this phase separation hasn't been really seen directly through imaging. And the technique of choice, we believe, to monitor the phase separation is this near-field nanoscopy. This is a technique developed by Fritz Kalman in Munich, and his near-field nanoscope is schematically sketched here. It's basically an A effect with the same cantilever that oscillates about the sample. This cantilever is illuminated with infrared light in far field, and scattered signal is also collected in far field. However, this signal contains information about what's going on a very local scale. Let's zoom at what's happening in this setup at the apex of the cantilever tip. When it's illuminated with light, you create a dipole at the apex of the tip, and you can, if you approach this tip to the sample, you also create a mirror dipole in the sample. And you can modulate this process by moving cantilever up and down. And one can show that scattered light produced by this system of the tip and the sample carries information about local values of optical constants at the wavelength of your source. And so then you can scan your sample with respect to this cantilever. You can build maps of local values of dielectric constant, local values of the conductivity with very high spatial resolution. The spatial resolution has nothing to do with the wavelength of light. Spatial resolution is now determined as by the apex of the alone, and this can be as small as 100 angstroms or even smaller. So in the best case scenario, this technique gives you a local measurement of the conductivity literally at the nanoscale. So empowered by this literally sharp technique, we thought we are in the position to go to the root of the problem of phase separation in vanadium dioxide. So in the next several diagrams, I will show you maps looking approximately like this. This will be maps of the amplitude of the scattered signal collected at the frequency of about 1,000 wave numbers. It's a very good frequency for VO2 because it's smaller than the band gap of the insulating, of VO2 in the insulating phase. It's smaller than the Drude activity in the metallic phase. So there is plenty of contrast between these two phases at this wavelength. So these maps will be collected from area of 4 by 4 microns with a spatial resolution of about 100 angstroms. And I will plot in this map the second harmonic of the amplitude of scattered light. And this second harmonic can be converted into the real part of the dielectric function. I will not spend any time on this conversion. What is important is that the small scattering signal is produced by regions where epsilon is positive. So the small scattering signal will stand for the insulating in these regions, and as soon as the dielectric function changes sign and you go into the regime of negative epsilon, you get enhancement of your signal, so these will be green and yellow and reddish regions. So below 341 Kelvin, not much is going on in VO2, but then if you warm it up a little bit, you start seeing first metallic puddles embedded in the insulating host. They grow in size, they grow some more. So here we are at the edge of percolation. Eventually these puddles percolate and form more or less homogeneous VO2. So this set of images shows the insulated to metal transition in progress, and the percolated nature of this transition is quite evident in this diagram. We reproduce these images at different wavelengths, and we still observe this percolated behavior. We do these type of measurements through multiple cycles across the transition. Some of these regions occur quite randomly, and at other locations, these images appear to be consistent and appear to be reproducible through multiple cycles. We also can correlate this electronic contrast with the real space information. Remember, this tool is just, in the first place, is an atomic force microscope, so we collected topographic images of these films. Our films are granular, and analysis that Alex Krenzel has done demonstrates that many of these newborn metallic puddles nucleate at the boundaries of grains. In other cases, if we zoom at one particular grain, we observe that half of the grain would switch into the metallic state, and the other would stay, other half would stay insulating. Here, red shows an overlay of infrared contrast, and black and white is topographic contrast. So basically, all these experiments seem to suggest that electronic phase separation in VO2 is an interplay between first order nature of the transition and lots of extrinsic effects that occur in this granular film. So now I will end. Now I would like to show these images together with resistivity data. So on the left-hand side we have homogeneous insulator. On the right-hand side we have somewhat inhomogeneous band metal, but there are no insulating droplets in this region. It is this intermediate region that is most interesting. That's where we observe this phase separated effects, and that is the regime where VO2 also shows this switching effects. Electrostatic switching in gated structures, and this current-induced switching of resistance that Tom Driscoll has observed. So I believe it's natural to suppose that electronic phase separation is really a precondition for all these switching effects that we witnessed so far in vanadium dioxide. So far we observed resistance switching and capacitance switching. Now let's zoom at one of these images close to the percolation. And in this image, the VO2 hasn't percolated yet, but this image may clarify why electrostatic switching here and current-induced switching has actually a lot in common. If we imagine potential difference applied to this hypothetical terminals, before the current will start flowing between terminals, you end up building the electric field across the region of blue insulator. So the picture of electronically driven insulated metal condition that we have in mind is the following. Current pulses of the electric field appear to be able to modify this percolation pattern in some form, either through local breakdowns or through promoting the growth of this insulating system. And because at the edge of percolation, the material is very unstable, you cannot really decide that it wants to be an insulator or a metal, and so it's very easy to tip the balance towards one side. We have not confirmed the growth of this domain by direct imaging. It may be difficult to do it for gated structures. It should be possible to do it for two-terminal devices, but experiments on memory capacitance that I will describe next are at least qualitatively consistent with this picture. Before I go to analysis of capacitance, I would like to show another group of images here, and this will be images of structural changes that we will do across the transition. So we are absolutely sure that the insulator on the left-hand side of this plot is monoclinic, shows dimerized vanadiums. We are absolutely sure that dimerization is gone on the right-hand side of this plot. We don't really know yet what is the crystal structure of these metallic products. And indirectly, many experiments suggest that electronic changes in VO2 may precede structural changes. But all this experimental evidence comes from area averaging techniques. And you can clearly see that we really need local probes to have conclusive information on this issue. And that's what we try to obtain together with my colleague Perco. So I will be showing you this type of images. This is the image of contrast in this image will be formed by the Bragg peak, by the intensity of the Bragg peak associated with the monoclinic phase. The area of these images is a little bit smaller than of the infrared images, but it's still substantially large, and this area is confined between two electrical contacts attached to the VO2 film, so we also know what happens to this region electronically. So red corresponds to the strong intensity of the monoclinic peak, and blue will correspond to the disappearance of this peak, and simultaneously the peak associated with the rutile phase will appear. So this series of images shows that the structural transition also occurs percolatively in VO2. If you do this type of experiment with a finer temperature step, you actually can register non-monotonic changes of the intensity of this peak, whereas all electronic effects happen monotonically. So a tentative conclusion that we have from all these data is that structural transition and electronic transition are really decoupled one from each other, and that these puddles, metallic puddles, can occur in either rutile or monoclinic form. So memory capacitance. So let's look at this image again. And with some imagination, one can imagine multiple capacitors here formed by metallic puddles separated with insulating material. And And the magnitude of this capacitance will depend on the fill-in fraction of metallic regions and on area separating these metallic regions. So if we can enhance the fill-in fraction with current pulses, then capacitance will change. So there are multiple ways to measure capacitance. We have an optics group, so we decided to measure it optically. And the idea for an optical measurement of capacitance comes from our work on metamaterials. Metamaterials are very interesting structures proposed about 10 years ago by John Pendry. This is one interesting implementation of metamaterials. These are split rings, metallic split rings that can be formed on some substrate. And John Pendry has been able to show that a ring like this acts as a small LC circuit. Inductance comes from current oscillating along this ring. Capacitance comes from this split in metallic ring. And he also has been able to show that these rings demonstrate strong absorption resonances, and then the frequency of this absorption resonance depends on capacitance in this ring and in the material surrounding this ring. So, while these split rings possess very interesting and non-intuitive electromagnetic properties, carried water flow is likely to be made out of these type of rings, as we might have heard. But leaving all that aside, the idea of the experiment probing capacitance in vanadium dioxide is the following. So we want to fabricate this array of these split rings on the VO2 film, and we were going to tune VO2 across the metal insulated transition with current pulses, and we were going to register the frequency of this resonance. So let's worry for a moment about dimensions of these rings. So we would like to squeeze few of these percolating grains in the split. And that means that the split has to be of the order of 10 microns. And back in 2004, we were able to show that gold rings like that, with splits of about 5 microns, demonstrate this resonance at about 30 wave numbers in infrared range. A frequency range that's very convenient for us to work in. So Tom designed and fabricated an array of split rings on VO2 film, and we are going to tune this VO2 film with current pulses. The resonance that this type of structure shows is pretty sharp, and much sharper than what we used to have back in 2004, and this is of course very helpful to for the idea of this experiment to register the resonance frequency as VO2 is tuned across the insulated to metal transition. So these are the data. So this is the frequency of the resonance. It's about 58 numbers for this particular structure. And then applying the current pulse, one can shift this resonance to a lower value. This implies increase of capacitance. Applying another current pulse, or we can shift it more, and so on. So note that it takes about several minutes to perform each of these experiments, and during that time, no current pulse is applied to VO2. And yet VO2 seems to be remembering its capacitance for quite some time at least, and capacitance is systematically increasing with the number of these pulses like the VO2 ones. So this experiment seemed to suggest the memory capacitance of VO2, and we were quite excited with this observation, of course, and also this experiment seemed to suggest that the resistance, memory resistance changes and memory capacitance changes of this type of devices are clearly connected one to each other. Tom and Max designed a very interesting switching element based on these new properties of VO2, and some other. In the next meeting, we were hoping to report more on the on this behavior of this switching surface. So I'm basically done with the memory part of our observations in VO2, and I would like to make some final comments on the nature of the metallic state in this puddle. This electronic state appears to be quite interesting in the sense that it is distinct from the electronic state of VO2 at high temperatures from this rutile VO2. And an interesting part of this state is in the temperature dependence of the effective mass. Effective mass of VO2 at high temperatures is not very different from that of most oxides. It's new free electron value. But it turns out that close to the boundary of the insulated metal transition, the effective mass is strongly enhanced. It's enhanced in nearly divergent fashion. We are able to measure the effective mass using the analysis of the optical conductivity. And this nearly divergent behavior of the effective mass, we believe, is quite significant. And significance of that goes back to the seminal paper of Brinkman and Rice back in the 70s. This effective divergence of mass is a signature of Mott transition driven by electronic correlation. Experiments performed on V2O3, canonical Mott insulator, also show very strong nearly divergent behavior of the effective mass, and we believe this result puts vanadium dioxide in the same category with VO2-3. So electronic correlations appear to be playing a major role in the insulating metal transition, whereas structural changes, we believe, are of secondary significance here. So let me summarize. I discussed three different facets of memory effects in VO2: persistent electrostatic switching, memory resistance, memory capacitance. We believe all these effects have a common origin. First, they all occur close to the boundary of the insulated metal transition, and importantly, in this regime, vanadium dioxide appears to be phase separated, and it's quite likely that reconfiguring of this phase separated pattern, either by the electric field or by electric current, we are able to switch VO2 between these persistent states. Electronic correlations appear to be played a major role in the phase transition, and so indirectly electronic correlations are also important for memory effects that we are observing here. A number of open questions. So the role of structural changes still has to be fully resolved. Ideally, one would like to measure the structure of one single grain, one newborn metallic puddle here, even with the current status of X-ray nanoimaging. It hasn't been possible so far. Hopefully, it will become possible in the future. We don't know if these effects can be switched back by all electrical means. So experiments that we have done so far guided us sort of downstairs, and with all electrical means we are unable so far to move on. We don't know if there are fundamental restrictions for that or not, but this is certainly an open issue. Everything we know about VO2 suggests that switching can be very efficiently initiated in light, and on very short time scales. And I think it would be interesting to explore if VO2 also shows persistent photoconductivity and persistent photocapacitance. Thank you for your attention.
Well, thank you very much for a very, very interesting talk. So, are there any questions? Alex?
Jim, I guess I'm not very clear understanding, but in your electrical switching, is that just not local heating?
Well,
and therefore you go and you your phase temperature?
So that's an important question. There is definitely no thermal heating in gated structures, and yet these gated structures can be switched electronically from from high resistance state to low resistance state. So heating is definitely taking place in this current pulse switching. Whether this is the only mechanism that is important, it's not so clear.
Okay, can I follow up with a question?
Yes, certainly, of course.
And so in your IR now measurement, you're looking at the surface of the sample itself, whereas with the X-ray nano, you're looking at the bulk, and you're nucleating a phase. So nucleation, depends on nucleation centers, and as a result, the bulk may look different than the surface. That's fully appropriate, and as a result, you may be seeing reality instead of not reality.
I agree with you. So X-rays can draw through the entire film, and that is the reason why it is so difficult to measure the structure, crystal structure of one of these columns. So we may be picking up nucleation regions close to the interface between film and the substrate, whereas in the near field probe we probe the top surface of the film. This experiment,
why when you do a current pulse, you may not see an effect there because it may be a bulk effect, not a surface effect.
Yeah, so this again we will resolve through direct experiments that are currently underway, and there should be a simple experimental answer to this question. We just haven't done that yet.
If you reduce the current pulse by say 10 times, and enlarge the period by 10 times as well, you get the same effect.
We haven't played with the period yet. So what the way this experiment is done is current is applied, and then we are just we are waiting and we are probing what's going on, especially in this memory capacitance experiment. The delay between subsequent pulses was many minutes that are required to measure this resonance.
So it's really the heating block of the thing that's switching it.
Yeah.
Is there an idea about the persistence time? Can this be compared to an initial calculation of the reality values and the creation values?
So far, time in this experiment has been limited by our patient. So I don't know about theoretical time.
Which was how long?
It's hours.
Up to most of the day. But
If I remember correctly, you're using silver electrons and bottom electrons in relation to inject the spectrometers from the oxide, right?
In gated structures, yes, we are using silver electrons.
Yeah, so I was wondering, what are the injection barriers between the silver and the corruption and balance and the vanadium dioxide, and also whether it's possible that there is some heating going on in the interface between the silver and the vanadium despite the gated structure.
So with I don't think heating is going on there, and even if heating due to the leakage through the gate insulator is happening, it's still not the driving force of what is going on. Heating is similar to the electron doped side and the hole doped side, but the effect of enhanced metallicity is definitely different. So we think that heating is not the dominant factor, and whatever are the work functions of silver with respect to the tool, they appear to be such that only hole injection is favored and the electron injection is not favored. I don't remember the numbers.
What's the injection mechanism? Is it thermally assisted tunnel to whatever area there is, or is it like to assisted tunnel?
So probably all of the above, and but the main impact of electrostatic changes, we think, is not just pure injection of charges, and that's because even in the so-called insulating phase of VO2, there are plenty of charges in VO2, and is comparable to what we can electrostatically induce. I think what is happening really is some reconfiguration of these metallic puddles that are preformed by increased temperature, and they are being impacted by the electric field. But all of the mechanisms that you mentioned are probably taking place.
Yeah, your X-ray patterns look anisotropic. Is that my eyesight?
Isotropic is what?
Well, I mean, they look really. Can you show them?
Oh yeah, that's a.
And so there's a directionality in them, which.
Yeah, it's
what does it mean?
it probably doesn't mean too much because this experiment is a grazing angle experiment. In order to graze for this graphic, you have to be at a certain angle, and so the spatial resolution of the probe is different along X and along Y. We try to correct for that, but you cannot fully correct it.
So I can't read anything into the shape of those.
No, I don't think shape is significant, at least at this level. So a circular metallic puddle will look elongated.
So if you were to exalt on that, you use
Yeah.
But nonetheless, the scale is actually quite different. I mean, it's a much finer scale.
One bulk, one surface.
Well, there are all kinds of reasons. It could be. I just want to check what really the data is saying.
So this grazing angle, I think, is a.
No, but the grazing angle presumably won't mess up the scale in the lateral direction. I mean, therefore, what you're seeing actually is something which is effectively spectral on a leg scale, which is quite a bit shorter than the. It's a finer grain scale. Just an optical illusion. Or is it? Maybe. I suppose we have a subsidiary which might be related, which is associated with. As you said, there's a structural aspect to this transition, which involves strain as well. So, how big is the sort of electrorestrictive component of the strain?
I don't know. And strain could be varying along the sample surface quite considerably, especially in this granular film. So grain boundaries are likely to be showing different strain from the theory of any particular grain. So don't know how to quantify.
Could be the strain
That's right, and I think that's an important factor, but that's not the only one, because this strain is sort of always there, so that we want to scan multiple times.
So the
variation,
local variation of strain will determine the width of the region.
could be, but not only by strain, because this I think strain will produce reproducible images through multiple cycles through the transition. But can we see that some regions are reproducible and others appear to be totally random?
So we have no question standing in the question?
I think it's moved now.
Oh, sorry. I think a question at the back, somebody?
Yeah, so like if you change the temperature, you see a certain hysteresis. Because you know, right, in the management position, so you can switch it back and forth. Is that correct?
Electrically.
No, just by temperature.
Oh, by temperature, yeah, you can always go, you can go back and eventually you erase this metallic state.
And then if you do your electrical experiment, are you within the width of the hysteresis loop? So or maybe a different question, somewhat related, can you erase your electrical effect by temperature?
Yes, we can.
You can.
So most of these interesting switching effects are observed somewhere here. Okay, and if you cool down the sample, yes, you do erase that. So it's not. So it still may be interesting for a number of applications if you design your device appropriately. But with all electrical means, we cannot go from here to here to the high resistance state. At least so far, we have not been able to demonstrate.
the strong probability, of course, when people are excited about electronic self-induced charge separation or charge inhomogeneity. As far as I understood, you really focused on the undoped, the stoichiometric DO2. Now, if you move away on the doping axis, is your inhomogeneous dead metal somehow destructive also for the behavior of the doped system, where it would be probably applicable for a much wider temperature range, showing switching phenomena?
We have just started working on doped DO2, so we don't really have real space results yet. But it's certainly a direction that I think is very interesting and hopefully illuminating on what's going on.
What are the possibilities to enlarge the window over which you have the stability of information? Pressure or visual reduction?
That is doable. If you work with the way you prepare your DO2 films, you can definitely broaden this loop by 30 Kelvin or more. So especially if you go to smaller islands, maybe strained islands, this has been demonstrated. So the range is quite flexible, and you can also move the temperature at which transition happens around. At least you can reduce it, not enhance it, but you can reduce it. So DO2 has plenty of flexibility as far as the range where it affects your
I have a question. In the case when the DO2 changes the structure from glucose to organic, and the interface between those two structural symbols very distorted. I wondered if anything on capacitance effects could be related to charge transfer structural difference. Why wouldn't that be important?
Yeah, that's certainly a possibility. So that's how we think of capacitance in terms of this. That's certainly a possibility that charge can be stored at these structurally different boundaries. Yeah. I think that what is happening, capacitance easily evolved in the space region. If we indeed are promoting growth of these regions with electrical pulses or with temperature for that matter. So capacitance appears to be enhanced, and that's what the resonance experiments that Tom Basov has done seem to show.
A quick follow-up. Do you have any idea as to what types of dielectric constant you observe?
Yes, we have a very good idea of what these dielectric constants are. It's certainly so. First of all, you can define dielectric constant for area average pattern, and that's one value you obtain. And this dielectric constant, area average dielectric constant, shows divergent behavior from divergent, meaning that it's increasing from about 10 to 120 before it goes to negative values in the valid phase. And also applying effective medium analysis, we can extract the dielectric constant of these models. So very strong negative values that and we have frequency dependence of the dielectric constant as well.
Okay, let's thank Dimitri one more time.